Okay, the first speaker of technical session 2 is Professor Jeffrey Herrmann from the University of Maryland.
Thank you, Michael. And thank you for the opportunity to be part of this event today. I appreciate it. And we're going to try to talk from here and use the clicker, and if that doesn't work, I'll move it back over there. But anyway, first of all, I'm Jeffrey Herrmann. I'm a professor here in the Department of Mechanical Engineering and the Institute for Systems Research. And I'm also one of the co-PIs on the Artemis Cooperative Agreement. And today I'll be talking about meta-reasoning. This topic that I'll be discussing today is based on a number of different research projects that I, my collaborators, and students have been doing over the last few years. And these projects have been sponsored by various organizations, including the Air Force Research Lab and the Army Research Lab. And I'm very grateful to my collaborators and students and sponsors for making this research possible. Today's talk is actually sort of synthesizing what we've learned from those research projects into a process that I call meta-reasoning engineering. At the very end of the talk, I'll kind of get back into research mode and talk about where we might want to go with meta-reasoning. But the first part of this talk will be more general. Okay, so first I have a shameless plug for my new book on meta-reasoning for robots, which just came out from Springer this month. And so some of the things I'll be talking about today are also discussed in this book. So just type in meta-reasoning for robots in your favorite search engine, and you should be able to find it. Okay, so we often talk about the benefit of robots in terms of their ability to do dirty, dull, and dangerous tasks to alleviate humans from having to do those things. And so here are just a few examples. Here we have a couple of robots exploring an underground environment. Here we have a tug robot that is delivering supplies in a hospital near St. Louis. And the nurses don't have to do that tedious work, so they have more time to spend interacting and helping their patients. Here we have an image from Skydio of one of their drones doing a bridge inspection, which is a dangerous job. And by using a drone, the bridge inspectors can stay safely on the shore. They don't have to go up and do that dangerous job. Now, a lot of these robots are going to need artificial intelligence in order to do these jobs autonomously, but there are problems with that. This is a quote from a recent report from the National Academies, as Damadni at USC talks here about some of the limitations of AI ML applications. They deal with novel situations poorly. They engage in abnormal system behavior. They struggle to adapt to changing contexts, and they have other problems as well. Okay, so that's one problem, is that these algorithms and models that we're using are not quite 100% there. And the other problem is that these autonomous robots and autonomous systems have limited onboard computational resources. This is an image of a Skydio drone, and there's some vital statistics about it. It has a flight time about 35 minutes based on its current battery. It has a certain mass, it has a certain processor, CPUs, GPU, RAM, which seem like a lot and enable the system to perform obstacle avoidance and waypoint following. But if we want these systems to be even more autonomous and do even more on their own, they're going to need more resources. And that becomes a problem, especially in airborne applications. But in general, as people who design robots, we always have to make these difficult choices about which algorithms to actually implement in our autonomy stacks. And we face trade-offs between the power of the algorithm in terms of its ability to come up with high quality solutions But then, the better algorithms require more memory, they require more computational horsepower, et cetera, et cetera. And no matter, we can always hope for better chips and better processors, and that's great. But at some point, we have to make a design decision. We have to decide what's going to go on board. We have to select the algorithms, and that becomes a limitation. So another option would be to delay making those algorithm design choices by giving the robot or autonomous system the ability to adapt its reasoning system, right? So instead of selecting a fixed set of algorithms and saying, okay, the robot, use those algorithms, we might want to give the robot the ability to change its algorithms dynamically. That's called meta-reasoning. So meta-reasoning is reasoning about reasoning, or deciding how to decide. It's something that we as humans do, and people have been studying meta-reasoning as a branch of artificial intelligence for quite a while. And now we're getting to the point where we can start actually implementing that on robots. This image here is from a book chapter by Cox and Raja in a book that's a great resource about meta-reasoning. And you notice it has 3 different levels: the ground level, the object level, and the meta level. To make that a little bit more concrete, we can think here about the ground level is the robot itself, right? The robot moving around in the environment, the robot using its sensors to detect what's out there in the environment. And then it sends that information up to the object level, which is doing the reasoning. So here we have a little schematic of the ARL ground autonomy stack. We've been working with that a lot lately. And that autonomy stack, like other types of autonomy stacks, can process the sensor data, it can do SLAM, it can do planning of different types, and eventually it can send commands back to the robot, right? So we have that loop, right? That ground level, object level loop. Now the object level might be a very sophisticated, autonomy stack, or it might be something simple depending on the type of the robot. But now we add a meta level to that, and the point of the meta level is to monitor and control the reasoning level. And that monitoring control might be a very simple rule-based approach, like a little schematic of a flowchart shown here, or it might be something more complicated. But the key thing is that the meta level, the meta reasoning policy in the meta level is monitoring and controlling the object level reasoning. And there are many different ways in which it might do that. It might be switching path planners, it might be changing task allocation algorithms, it might be reacting to unexpected situations, it might be changing the parameter values of the algorithms that are used, it might be offloading computation to some other resources that are available. Or it might be just stopping a search algorithm to say, okay, we've got a good enough solution, let's move on. There are many different ways meta-reasoning can work. In this figure is emphasizing just a single robot, but meta-reasoning can be done in multi-agent or multi-robot systems, which we've done in the past as well. Now, so the next thing I'm going to talk about is basically meta-reasoning engineering, which is a process of doing meta-reasoning. So I've got a robot, it's got to do some mission, and I think meta-reasoning might be helpful to help that robot perform its mission more reliably, or to make it operate more safely or more efficiently, whatever it is, okay? So here we have these 4 steps of meta-reasoning engineering, and they're shown here as a simple sequence, but we know in any engineering process, we might need to have iteration, right? We get to one step, we realize something's wrong, we need to go back and redo something. But it begins with identifying the reasoning processes that should be monitored and controlled, right? Usually there's going to be some critical reasoning processes that are most important in the robot's performance, and we want to monitor and control those. And we need to identify that. That might be might be through experiments, or just through our experience, or by some analysis of the computations. Then we need to determine the meta-reasoning architecture, And that includes the meta-reasoning mode, which I'll discuss in a minute, and the way that the meta-reasoning is going to be implemented. We then need to synthesize the meta-reasoning policies, and then we need, of course, to test the meta-reasoning policies and evaluate them to see if they're actually making an improvement. Or we might have multiple policies, and we want to see which one is the best. Now, in terms of the meta-reasoning architecture, it incorporates the meta-reasoning mode and the integration or implementation. So the meta-reasoning mode describes what is specified or modified as a result of meta-reasoning. So algorithm selection is a classic meta-reasoning problem. It's been studied for many years, and we've implemented that ourselves. But there are many other ways that meta-reasoning can work: parameter adjustment, policy adjustment, offloading computations, a whole bunch of different things that people have developed. And of course, there's always room for more ways of doing it. This is certainly not a comprehensive list. Okay, then we need to think about implementing the meta-reasoning. Well, there's different ways in which we might implement it. Here we're assuming that the robot has some kind of autonomy stack that's running on the robot on some kind of one or more processors. Well, we might implement meta-reasoning as a separate process on that same computer, or even on its own computer. Maybe meta-reasoning has its own resources. Or as shown in the middle figure, we might implement it as part of the autonomy stack or a module in the autonomy software, right? Like in that ARL ground autonomy stack, which is ROS-based, we might implement the meta-reasoning as another process in that autonomy stack. And on the far right there, we might actually decide to integrate the meta-reasoning directly into the reasoning algorithm, make it actually part of the optimization algorithm or the perception algorithm. These are different ways of implementing it, and they're trade-offs, mostly about the benefits of integration in terms of speed versus the benefits of modularity, right, in terms of making it easier to modify. But it's one of the choices that has to be made. Okay, so now we've got the meta-reasoning architecture. We need to now synthesize the meta-reasoning policies. And we can use a data-driven approach to that. So here we have a number of steps in the synthesis process. One, we need to define the state variables and the performance measures that we're interested in, and we need to identify the set of reasoning options. So it might be a set of algorithms that we're interested in doing algorithm selection, for instance. Now, once we've determined that, we then need to do some experiments or some analysis. In some cases, we might be able to analyze directly and determine the performance of the different reasoning options. In other cases, we might want to do simulation experiments, or we might want to do field experiments in order to characterize the performance of the reasoning options and develop or gather data about their performance. And then we need to go into synthesis, where we actually analyze that data to create the meta-reasoning policy or policies. Now, this might be using some type of machine learning approach to develop some type of regression model or some type of classifier. It might be doing more traditional statistical analysis, or it might even be by inspection, by looking at the results, and some exploratory data analysis shows us clearly what the meta-reasoning policy should be. Once we've synthesized one or more meta-reasoning policies, then we can go on to testing. And we might go back and do those same experiments again, but now with the meta-reasoning policies, in order to see, does the meta-reasoning policy improve performance? When does it improve performance? And answer those types of research questions. So again, those 4 steps of identifying the reasoning options, determining the meta-reasoning architecture, synthesizing the meta-reasoning policy, and then testing the meta-reasoning policies. Now I'd like to turn to a specific project that we've done recently that kind of illustrates these ideas. Okay, so this is a project that was a task that we did as one of the Artemis projects, which is sponsored by the Army Research Lab. through the Artemis Cooperative Agreement. Our students, Sydney Molnar, Robbie McPherson, Matt Muller, and Lawrence Rhodes, did the software implementation and the testing last summer. The problem that we discovered as we were experimenting, doing simulation experiments with the autonomy stack, was that the robot would get stuck. So here's an image from the Unity simulation of a simulated warthog running the ARL ground autonomy stack, and it's stuck behind some trees, and the global and local path planners that it's running as part of the autonomy stack are unable to come up with a solution to get the robot around the trees and back headed towards its goal, okay? And this happened in different situations. It seemed to be a unnecessarily common problem, and we decided that we would try to attack this problem using meta-reasoning. So right off the bat, we knew what the reasoning process was. It was the global and local path planners. So this is a more detailed schematic of the ARL ground autonomy stack, and you can see that it has perception, it has SLAM, it has mission planning, and it has motion planning. And it has a navigation manager that operates a global path planner and a local path planner. And the two of them work together to get the robot to where it's going. The autonomy stack already has a number of different path planners in its library. We didn't invent any new path planners. We were just using the existing ones that the ARL researchers and other people had developed and were available to the autonomy stack, okay? But we decided that we would look at using meta-reasoning as an algorithm to do algorithm selection over those path planners. So that was the meta-reasoning, that was the reasoning process that we wanted to control. Well, now in terms of implementation, because of the ROS architecture here, we decided that we would just implement meta-reasoning as another node in this ROS system. In the meta-reasoning mode itself, we can formulate as a meta-reasoning problem, as shown here. We have state variables, which are the current status of the path planners in terms of whether or not they're able to come up with a solution. We have a bunch of reasoning options. And remember now we need combinations of planners because we have to have a global path planner and a local path planner. And we looked at different combinations, and some of them are listed here. And we had performance measures. We wanted to know how was the robot able to get to its goal, and how long did it take the robot to get to its goal? Okay, so that's kind of the meta-reasoning problem. Okay, well, the next step in our process is to characterize their performance. So we then conducted a number of simulation experiments. This is sort of a top-down view of a simulation environment in Unity. You can just ignore the straight lines there. But we have a simulated village with a simulated market, with a little market area, some forested areas off to the upper left and upper right. And then these blue dots and the red dashed line show one of the routes that we were using in our testing. So we took all these different planner combinations, we ran them on multiple scenarios in our simulated environment, and then we characterize their performance in terms of which ones had the best performance in terms of the robot getting to the goal. Well then, based on those results, we did a pretty simple synthesis process. We didn't do anything really fancy here. We just looked at which combinations performed best. And then we synthesized some meta-reasoning policies. We developed 2 sequential policies. So in these sequential policies, the robot starts off with one combination of planners, and when that gets stuck, when the robot gets stuck and the planners are unable to come up with a solution, it switches to the next combination. And if it gets stuck again, it switches to the next combination. Then it goes through that, and if it gets to the bottom of the list, then it goes back to the top and starts over. Okay, so it's sequential. We had 2 different versions of that, one based on the different performance measures, time to success and success rate. We also had a parallel policy that stuck with one global path planner and ran 3 different local path planners in parallel, and then the meta-reasoning algorithm chose which solution to use. Okay, so we were able to implement all of these in a meta-reasoning node in the in the ARL ground autonomy stack. So then the last step is to do testing. And so we did some testing last summer on the different meta-reasoning policies. So here in this table, we have the different planner combinations. And then at the bottom, we have the different meta-reasoning policies. We had 3 different scenarios. We did, I think, we did 30 runs in each scenario, and we calculated how often the robot was able to get to the goal. And we found that the meta-reasoning policies, improved the likelihood that the robot would actually get to the goal location. Okay, so that was a positive result. We're happy about that. But we have a lot more to do. We're continuing to work on this. We're currently implementing this on a ClearPath Jackal robot. We'll be taking that up to Grace's quarters this summer. We're looking at more simulation experiments, different conditions for triggering the meta-reasoning, different policies based on the surrounding environment and other factors that might be relevant to improving the path planning. So in this project, we were able to go through all those different steps and ultimately develop some successful meta-reasoning policies. Okay, so the benefit of this, from a robotics point of view, is instead of picking one combination of path planners and kind of sort of being stuck with that, the meta-reasoning allows the robot to switch between different combinations on its own, right, in response to unexpected situations or in response to path planning failures. Okay, so from the designer's point of view, this is great. I don't have to pick one and hope it works, right? I can let the robot pick the path planners dynamically, right? Makes it more intelligent. Okay, so so what's ahead? So ultimately, we can think of meta-reasoning as a process that optimizes the use of the computational resources that are on board the robot. So this image is sort of a schematic or an illustration of where I think we might be headed with meta-reasoning. Now, one step at a time, right? We can't just jump to this kind of comprehensive optimization problem. It's not very practical yet. But we can at least propose to model the object level reasoning, which is a type of process, right? Perhaps stochastic, and it's controlled by which reasoning processes are operating. Okay, so we might model it as an MDP. Well, then if we can model the object level reasoning as an MDP, then the meta reasoning problem is to find the optimal policy, right, for that MDP, right? Conceptually, that's not too strange. It's just that how do we model that object level, right? There's a lot of different computational processes going on in a complicated robot, right? A lot of different processing units, memory, power, different reasoning algorithms, right? Developing a model of that is going to be quite a challenge. But that is one thing that we're thinking of doing in the future. Finally, I'd like to conclude just with a list of some of our recent publications on meta-reasoning. And just to sum up by saying that, in our work and in the work of other researchers and other schools and other labs, right, we're beginning to show, we're beginning to see that meta-reasoning approaches can improve the performance of robots and autonomous systems. It can make them operate more safely, more reliably, more efficiently. And as I said before, it defers that design decision so that we allow the robot to adapt its reasoning processes instead of fixing them at design time. And with that, I will stop and I'll be happy to take any questions if we have time, Michael.
Yeah, thank you, Professor Herrmann. We have time for a couple of questions, and can the next speaker start coming up and getting set up? You can just plug your computer into the same plug that that one's plugged into.
Hi, thanks for the talk. I was wondering, are meta-reasoning processes, or can they be self-reflective? Can they decide that they're not gaining enough benefits to be worth the computational cost of running the meta-reasoning process itself?
That's a great question, because it definitely, meta-reasoning does add a little bit of overhead, and that's why in our work we've tried to focus on very lightweight meta-reasoning policies. I have not seen a meta-reasoning policy that is self-reflective and knows to turn itself off. At one level, that would be a meta-reasoning policy, right? Because now you're controlling the meta-reasoning process. It's certainly possible to do that. We haven't tried it, though. It'd be interesting to study. Thanks.
From like a CS background, it seems like there might be a lot of overlap between, you know, programming meta-reasoning policies and like how operating systems handle concurrency. Is there any kind of like overlap between, you know, in terms of like how you manage hardware resources,
right,
and stuff like that? Is there kind of any overlap between people in these sorts of fields of research, or?
I would say at a very high level there is an overlap, you know, at a conceptual level, but the work that we're doing and the work that other robotics people are doing on meta-reasoning is not focused on the actual hardware, right? That's a different type of problem, and we're not focused on that. We're focused on controlling the reasoning processes themselves.
But say you had like multiple like running, you know, reasoning processes that are all trying to solve the same problem concurrently.
Sure.
Like, would there be any way like to see if like to have a meta reasoning policy, see how efficiently all of those are running and whether they're coming to a solution, or?
Yes, that would be a meta reasoning policy. If it's monitoring the reasoning, the processes, those algorithms you mentioned, if it's monitoring them and then controlling them by, say, deciding when they should stop searching, or by picking the solution from one algorithm and ignoring the solutions from the others, that would be a type of meta reasoning. Yes, we can view it as meta reasoning.
Okay, thank you.
Sure.
Okay, let's thank the speaker one more time.
Thank you.